zoomed out. I will be honest.
We have some nice little demonstrations back here to visualize them. Let me just pull these over.
Oh, and dude, I asked Will the same question. You ever put that outline I made of you in your dorm? Pet. Bet. No,
Yeah, let's
because
put
I
it
was
on the
asking
floor so
Will,
a
and
little easier
he
to
said he
see.
hasn't done that yet.
Okay, so we've got a couple of visualizations up here. The one on the left is visualizing position. The one on the right is representing like a vector direction. So we're going to talk about vectors today. We've talked a little bit about vectors already. They're literally just three floats. So you all know what a float is. It's just a number. Can be negative, can be positive, can be zero. It doesn't have to be whole numbers. It can have decimals. It can go really big. It can go like really low. It can go very small. The vector, specifically vector threes are the only type of vector we have in Rec Room. You can literally just think of it as a sequence of three floats. There's just three numbers in a row. There's an x component is the first part of it, the y is the next one, and then z is the third one. In Rec Room, they'll always be in XYZ order. Some other platforms kind of have like their own order, like for instance, Unreal Engine, they go slightly different order. They are still XYZ, but conventionally, at least in Rec Room X, you can think of it as like left or right. Well, first I should explain that vectors can represent a few things. We usually use them for like doing 3D operations. So for instance, you could represent a position with a vector. Like I'm standing somewhere in this room, I have a coordinate, my position is a 3D vector. And that's what these things here are for. So if I take this ball, this text up here should be showing the position of the ball relative to that origin point. So you can think of this as 0, 0, 0. Every room, every coordinate space has a 0, 0, 0 point. This is referred to as the origin. They're everywhere in some room. For this little visualization, we're doing some math to treat that as the origin for this ball. So this is rounding to whole numbers. In reality, there'd be a bunch of decimal points there. But you can see as I move it up, the y number goes up. I can even move it down. It'll be a negative number on the y. As I move it this direction, you can see this is along the red line. Red is x. So x is left and right. One direction is positive, one direction is negative. Usually right is positive, left is negative. I guess it kind of depends where the reference direction for this little visualization is. But as I go here, yeah, you can see that's negative and then right is positive. So that's great. Similarly, we have Z. Z is forward and back conventionally. Forward is usually positive Z. Backward is usually negative Z. So this looks like it's actually, we're looking at the back of it. So as I move it this direction, we'll see negative Z go down, and move it this direction, it goes positive. And lastly, we have Y. Y, I guess, actually is the middle number. So as I move it up, you can see that one go up. This is the yellow. These colors, by the way, are consistent throughout all of Rec Room. Like if you take out your Maker Pen, select like the transform tool. Yeah, transform and click on something. You'll see that same blue, green, and red color scheme. Those represent these same axes. Cool. So that is a representation of using vectors to represent positions. We can also use them to represent directions. So directions is actually very similar. You can think of it as a vector pointing, like this is literally an arrow pointing at this thing, pointing at this ball. So as I move the ball around, you'll see it'll move. Just to face that. Something that kind of like is more useful in dealing with vectors that represent directions versus like positions is we have the magnitude. The magnitude, you can think of this just as the length of the vector. So this visualization here is going to create a directional vector, like an arrow pointing from the origin to this ball. This arrow is obviously limited to just like that same shape. So as I move it out, you won't see it get longer, but the actual, you'll see the magnitude get higher because that is the length from here to here. So you can think of it just as this line. And as I move closer, it'll get smaller. You'll also notice that if I move to this side, like you might think it would get negative, but it actually doesn't because like it's a length. Lengths can't be negative. It's not conventionally. So it'll just flip around and be that long in the other direction. Similarly, we have the X, Y, and Z. And then, there is a normalized value here. So I explained that as I move it further away, the vector gets longer, right? But it does still have a direction. Like if I have a vector here, that's kind of short, it's pointing this way. If I move it way out here, that's pointing about the same direction, but it's a way longer vector. The magnitude is much bigger. So if you don't care how long it is, like maybe you just want to point somewhere, you don't care like how far away it is, you can normalize it. Normalize it means you take the vector and you scale it. Like if it's a big vector, you scale it down. If it's really small, you scale it up. So the magnitude is exactly 1. Right now it's 12. It's rounding, so it's about 12. Normalize, this is the same as this, except it scales it down by about 12, since that's the magnitude. So it'll scale it to be the same direction, but it'll adjust the magnitude so it's exactly 1. And this can be useful for some math operations we'll get to later. Cool. Any questions about that? Okay, cool. I should explain, by the way, to calculate the magnitude, like for instance, if I put it here, you'll see this is 1, 2, 3, 4, 5, 6. 6 magnitude away from the origin. That's simple. It's a straight line. If I put it here, however, or I guess do it here so it's a little easier to see. So this is 6 units out in x and 6 units up in y. So how do you calculate the length of this line? You'll use something called the Pythagorean theorem, which we'll cover in a bit. It might sound kind of complicated, but basically all you do is you take each axis. So you take the x, this is 6 units, the y 6 units. You take the x, so 6. You square it, so 6 is now 36, and then you have 6 here. That's also 6, so 6 squared, also 36. That's 72. You take the square root of 72, and that is the length of this line. If I were to put it here, this is 6 in every direction. You would just do the same thing, 6 squared plus another 6 squared for the z, and take the square root of all of that. And that's how you get the line. There's a chip to do this for you, so you don't have to worry about the math. I'll get to that in a second. Cool. And that's pretty much everything for those little visualizations. Let me pull out some chip.
I didn't come in this class alone stuff that I hate in normal school.
Don't worry, you got this. Ooh.
Okay, so these are just about all the relevant vector chips you'll need. There might be more, but they're not too important. So to start with, I'll go over some that you already are familiar with. We have vector variable, and we have vector list variable. These work exactly like every other variable you've used, or list variable. I guess I should point out that you'll notice these don't have, like, if I were to take, for instance, a float port, there's a little value you can type things into it. Vectors unfortunately don't support that. So you got to use a vector create chip. Where is that one? Vector create, we'll get to that in a second, but it's pretty simple. There's vector list, works the same way as any other list variable. Down here, we have add, subtract, multiply, and divide. You've all seen these chips before, so they're nothing new. They just also happen to work with vectors. So if you add 2 vectors, if I have, like for instance, if my hand is the origin, and then I have a vector here, and then a vector here, and I add them, it'll go out even further. It'll just take their positions and add them on top of each other, as if like the last vector was the last origin, and you're just moving out relative to there. Subtract is the same thing, but in the opposite direction. Multiply and divide, these technically support vectors, but like there's not really any mathematical justification for that. That's not usually something that you do. I've never seen somebody do that, and there's probably not a good reason to. These chips ideally should not support vectors, so generally just don't worry about it. We have inverse lerp unclamped, lerp, and lerp unclamped. Have we gone through these chips before, like at all in this class? We haven't? Okay. These work the same as they work for vectors as they do for everything else. So none of this is specific to vectors, but since we haven't covered them before, I'll just talk about it briefly. So lerp, this stands for interpolate, linear interpolation specifically. It takes a start value, start port. This is just some port. It could be like float, int, vector. Yeah, I think those are the only ones. Let me check. Okay, they do also support colors, so you can interpolate between colors, which is kind of cool. And there's an end port, has to be the same type as the start port, and then you give it a progress value. This is a float. Normally, you will give it a number between 0 and 1, and there's a result port. This will give you the interpolated result between start and end at the progress level of interpolation. So if I, for instance, give it like 10 as the start, just like an int 10, and end is just an int 20, and I give it 0, it will go 0% of the way from 10 to 20. So that will just give you 10. If I give it 1, it'll go 100% of the way from 10 to 20. So that's just 20. If I give it 0.5, it will go 50% of the way, halfway between 10 and 20. So it'll just give you 15. It's also a float, so I could just give it like some very irrational number, like point whatever, a bunch of decimals, and it will figure out the math, go that far between them. For vectors, it's the same thing, except instead of one dimension, it'll do it for all 3 dimensions. Lerp unclamped is very similar, except that this one will, if you give it a number more than 1, it will give you the end value instead of like going out further. Same if you give it a negative value. You can think of it as like this. Like this one will clamp your progress value between 0 and 1. This one will not. So if I give this a progress value of 2 for 10 and 20, it would actually go all the way out to 30, whereas this one would just end at 10. We have inverse lerp and inverse lerp unclamped. These can be pretty useful, but I won't go into them too much. They're just the opposite of these things. Like you give them a result is your value, and then a start and end is the same as here, and it will give you the progress value. So it's kind of just doing the operation in reverse. You probably won't need that in this class. Okay, so we have a few more. These ones are pretty useful. First of all, you're probably going to want to use a vector3 create a lot. This is a very commonly used chip. This takes an x, y, and a z, and notice they're floats because, as I mentioned earlier, vector3s are just 3 floats together. It will take those values and just wrap them into a vector3 value that you can just use with any of these chips. Similarly, this probably should have been closer to that chip, but we have vector3 split. This does the exact opposite of vector3 create. You give it a vector, and it will split it and give you a port for the x, y, and z, like float set components. Cool. We have vector3 scale. This will take a vector. You just give it a vector value here, and a scalar number. This can be either an int or a float. So if I give this a vector, which is just like 1y, 0x, 1y, and 0z, just like pointing up 1 meter. By the way, for any of the chips that involve like Rec Room space coordinates, the units are always in meters. So if I have a vector representing a position 1 meter up from the origin, or just like 0, 1, 0, that will be 1 meter up from the origin. It's not feet, it's not anything else, it's just always meters. So if I give that like 0, 1, 0, and then I give that a scalar 1, it's going to multiply that vector. It's going to take the length of the vector and multiply it by 1. Now, if you multiply something by 1, you'll have the exact same result that you started with. So this will just be 0, 1, 0 again. If I give this a scalar 2, it will multiply it by 2. So 1 times 2, of course, is 2. So this would be 0, 2, 0. Those are obviously very simple examples. If I gave it -1, for instance, it would kind of invert it. So it would be like 0, -1, 0. And it supports floats. You can do like floating point numbers with lots of decimals, whatever you'd like. Vector3 closest point on plane. This one's kind of self-explanatory, at least conceptually in terms of the inputs. You give it a position in the room. You give it a position of a plane. If you don't know what a plane is, just think of like a 2-dimensional surface that just extends infinitely. So a position on that plane and a normal. You're probably going to see normal a bit more in this class. Normal just means perpendicular. So if you think of the floor plane, like the floor in this room, the normal vector to it is a vector sticking out of it, sticking up like up straight out of the ground. If you look at this wall, the normal vector is sticking straight out of it like this. So if you have the position and you have the perpendicular direction, mathematically, that's all you need to create a plane. So you give it a position and then these 2 values to define the plane. It'll compute on its own the closest point on that plane to the point. So if I, for instance, had a plane like this wall and I give it a point here, you can think of it as just like giving it like the point on this wall here. It would like something like this coordinate here. That's kind of a more advanced chip. I wouldn't expect you to need it anytime soon, unless you're making something fairly complex. Down here we have vector 3 cross, vector 3 dot. This is a cross product and a dot product. These are ways of multiplying vectors. Now, if you have two floats or two integers, and you want to multiply them, like I'm sure you all are familiar with that. That's a very simple operation. There's only one way to multiply integers and floats. Vectors have two conventional ways to multiply them. They do slightly different things. The dot products, first of all, you'll see LHS and RHS on both of these. That just stands for left-hand side and right-hand side. So if you have like, like a number and then like a time symbol and another number, one's on the left, one's on the right, that's all that means. The dot product, you'll give it two vectors and it will effectively just give you, so if I have a vector going like this, like one arm, and another vector going like this, it will give you the angle between those two vectors. So if they're like this, it'll give you something like 90 degrees. I think I would hope it's in degrees. It'll give you the angle between them. If they're very close or almost parallel, it'll give you a very small number. Cross product is a little bit different. This will give you a new vector. You'll see this one gives you a float. Cross product gives you a vector. So if you take the cross product of two vectors, it will give you a vector that is perpendicular or normal to those two vectors. So if you have any two vectors that are not parallel, you can imagine that there is only one plane that those two vectors can fit within. Like for instance, the most obvious example is if I have a vector going up and a vector going to the right, the cross product would be a vector perpendicular to that, so that would mean it's going out. If you think about it, like it could also be going out the other direction. It could be going behind me. That is determined by the order. If you switch the order, it will be the same direction. It'll just go the other side.
All right.
Cool. So we've covered those. We have vector 3 project and project on plane. These are very specific, so I'm not going to cover them in this class. But if you'd like to know about them, you can ask me afterward. Distance. This is a very useful chip. You give it two. You'll notice these are white ports. They're not strictly required to be vectors because they support a whole bunch of things. They support objects, players, and vectors. So if you give it, and not only that, but the two ports don't have to be the same thing. So you could give it one player, you could give it an object, you could give it a vector or a player, and an object, any combination of those three. And then it will tell you the distance between them in meters. So if I gave it a vector, like the position of this camera point, and then a player for myself, it would tell me how far apart it is. So if I get close, it'll be a small number. If I get far enough away, it will be a larger number. Cool. If I take the noise chip, this takes a vector 3 point, and then there is a result float output port. The point, you can think of this as, it's called Perlin noise, is the algorithm powering this chip. You can think of it as, so we covered the random chips earlier. Did we cover random chips? Okay, we covered random, cool. So you can think of it as that. It is random, except it's kind of a smooth random. So think of it as like a smooth wave that kind of goes up and down, except instead of being like you give it an X and it gives you a Y, you give it a 3-dimensional value and it gives you a 3-dimensional like smooth value back. So if I, for instance, were to give it, if I were to like give it noise values corresponding to a position in the room, and then I had, I don't know, like a beacon that would change its height based on the output of this result as it moved around. It would never like teleport to another height. It would always smoothly be moving up and down. So it's kind of nice to like animate things if you'd like.
So,
was there a question?
over here.
Oh yeah, what's up, Wolf?
So it's kind of like a lerp then?
It's similar to lerp in that it is smooth. It's a continuous curve, but it will kind of just be like random peaks and valleys as you move throughout the noise field.
Okay, that makes more sense.
Over here, we have get closest and get farthest. Internally, these actually are running the same thing as the distance chip. They're kind of similar. You give them an origin. This is either, I think, again, either an object, a player, or a vector. This is just one port. There's one value. And then below, you'll see the next one, targets. This is a list of, again, either players, objects, or vectors. Does not have to be the same type as origin. And then it will run its logic. It will check the distance from the origin to each value in the list of targets using the same logic we use in the distance chip internally. And then it will tell you which item in this list is closest. It will then tell you the index in that list. So if I give it a list of 5 items and like the very first one is the closest one, the index will be 0 because that's index 0 in that list. And then lastly, it will tell you the distance. Technically, if it were to just give you the index value, you could take that index and use index get or list get element from the same list you gave it to get the closest, and then you could do the distance chip from here to origin to the closest, and it would give you the distance. But they're just provided to make things a little bit simpler. So that's a great way to see which object is the closest to a group of other objects. Get farthest is almost exactly the same, except instead of telling you which one is closest, it tells you which one is farthest. Cool, let me cover these ones here. We have vector get magnitude. So I was showing you what magnitude was earlier in that visualization. This is that chip that will run the Pythagorean theorem for you. It will take the square root of the difference in x squared plus y squared plus z squared and compute that as a float and just give that to you. So if I have a vector that is very big, this will be a large number. If it's like a short vector, this will be a smaller number. Vector 3 normalize. You were seeing that normalized vector in that visualization earlier. This will just automatically normalize the vector for you. You could do the same thing if you didn't have that chip. You could use vector scale. Over here, yeah, right here. You could just take it and you could scale it such that the new magnitude is 1 instead of whatever it was before. You'd have to give it 1 as a proportion of the previous magnitude. This is kind of just nice. It'll just do it for you. And the vector 3 clamp magnitude, this is similar to normalize in that it will change the magnitude, but instead of making it exactly 1, you give it a maximum value. And if the vector has a magnitude longer than that value, it will scale it down to be that value. Cool, I think that's most of them. Are we missing any? Oh, transform and inverse transform. These are kind of more advanced. You can think of it as if I have, actually what we were doing in that visualization before, where as I would move the ball, it would show you the transform, like the vector, the position of that ball relative to the origin. I don't think these chips existed, so it's kind of something custom there. But what these chips generally do is they convert a vector space from, if you have like vectors in the room, it's by default relative to the origin of the room. You can use this and convert it to be like relative to another object. So for instance, if I wanted to treat, I don't know, like this position in the room as the new origin, I could use this, and instead of getting my position relative to the room origin, it could be relative to that. There's some ports on here. It's not too important. We probably won't use that. Cool. Oh, down here, I have not covered these ones yet. Inverse, this is the same as doing scale with a scale of -1. It will just flip the vector and make all of the components negative of what they currently are. So if I have like 0, 1, 0, it will just flip it. So it'll be 0, -1, 0. If they're negative, they'll flip to positive. If they're 0, they'll be unchanged. Yeah, what's up, Wolf?
If the positions are already negative, did that just change it to positive?
Yeah, exactly. If you have negative components on the vector and you take the inverse, you can think of it as flipping it to the other side of the origin.
Okay.
So if it's facing one direction, you take the inverse, it'll be facing the other direction.
Cool.
We have vector 3 move towards. This is kind of useful if you're animating things. You give it a current position, a target direction, and then a maximum delta. And it will take the current position, and this is kind of like lerp, except instead of lerp being normalized, like the start point is 0% and the end point is 100%. This will actually, instead of like going in percents, it'll go in meters. So you don't need this. You can like get the same logic built without it, but it's kind of nice if you want to. Max delta is how far you want to move from the current to target. So if I'm here and I want to move that direction and I give it a max delta of 0.1, it will move 0.1 meters in that direction. And if I run it again with that as the new current direction, kind of like starting over, it'll again move 0.1 until it gets there. If it's closer than the max delta away, it'll just go exactly to target. Smooth damp is kind of similar, except it's a little fancier. It has all these extra parameters like velocity, smooth time, max speed, delta time. We're not going to use this, but basically what it does is it animates it. Like if I start moving, if I'm here and I start moving this direction, that's going to I'm just going to instantaneously like start going at some speed. I'll go from going at 0 miles per hour to whatever speed I'm going in the next frame. So that's not the most realistic way things move. This will kind of accelerate it. It'll start completely still. It'll start gaining speed until it starts going at full speed, and then as it approaches the end, it'll slow down. So that is a nice ship to make things look nice as you move them, but it's a little bit more advanced than we will probably need here. Cool. I think that's everything here. Do we have any questions?
I do.
Yeah, what's up, Wolf?
Can you just explain again what's vector 3 clamp magnitude?
Yeah. So vector 3 clamp magnitude, you give it a vector and a max length.
Mm-hmm.
If I give it a vector, which say it represents direction, you can, like some, as I mentioned earlier, some vectors kind of represent positions, some represent directions. Depending on the context, you can kind of use them interchangeably. It's not like a strict requirement or like some internal data on like what it is. But if I have some vector, say it's like a 5 meter magnitude vector. If I give it a max length of, like, I don't know, 2 meters, it'll scale it down so it faces the same direction, and then has a magnitude of whatever I gave it. So if I gave it 2 meters, it would scale it to have a magnitude of 2. So you can think of it as either run it like also running normalize on it, so it has, you'd scale it to have a magnitude of 1, and then if it was bigger than the max magnitude, it will then scale it up to be a vector with that magnitude. Does that make a little more sense?
Mm-hmm.
Cool.
Thank you.
Cool. Any last questions before we get to the example? Yeah, what's up, Crypto?
Dude.
Yeah.
Yeah, so the inverse chip, you give it a vector, and you can think of it as like this vector is either facing some direction or some coordinate away from the origin. You can think of it as it moves it to the opposite side, both or all in x, y, and z. So if this is the origin and this is my vector, and I take the inverse, it would go over here. Just multiplying it by -1, basically. Cool. Okay, cool. Let's get to the example. Let me move all these chips back.
Nice.
Okay, so we're going to make a pretty basic UI, or AI, I mean. We're going to have an object which follows you around. It's kind of like the most simple AI you can have. Say I'm standing somewhere. We have some object off somewhere else in the room, and we want that object to move in the direction toward us. We're not going to worry about if there's a wall in the way or anything like that. That is a possible thing you can do. Actually, next update, the Pathfinder is coming out, which is going to do it all for you in rooms too. But we're just going to do a simple, very simple implementation that just takes the vector. Do you have a question, Default?
So, isn't it kind of similar to those pet things that people make? Like where
Yeah,
you can
probably.
Because that's
It
exactly what
depends
it sounds
specifically
like.
what you're talking about. But if you have a pet that is just walking toward you, that's probably what I would do if I were making a system like that in a room.
Right.
Cool. So let's put down just a little triangle shape.
Ew, it's chocolate.
Wait, okay.
Do you have a vanilla one? I'll take the
Okay,
vanilla one.
let's just rotate this a little bit and move it over here. So
Oh.
this is just going to be the object we have that's following us. Cool.
Here you go.
So that looks good. I'm going to configure it, by the way. I'm going to hit configure, click on the thing,
All right, thank you.
and there is a very important toggle we have to turn on. If I scroll to the bottom, advanced settings can modify with circuits. I'm going to turn that on because otherwise, if you try to move an object that does not have that enabled, it will not let you move it. So first things first, we're going to move it. We want it to continually be moving. The best way to do that is with a 30 hertz chip. So let's take out an event receiver. Okay, let's configure this to update at 30 hertz. Cool. So this is just going to be running continually. So let's get the position of the object. First, I'm going to tag it so I can find it in circuits.
Mhm.
I'll just name it AI, just the tag AI. Now let's take out a get first object with tag chip so we can get it.
Wait, we're tagging the like shape that you put down?
Yeah, I put a tag, it's just called AI on that shape. And now I'm going to type that same tag into this chip so I can get it. Cool. So now this is no longer an invalid object. It's giving me a reference to the shape. Next, we're going to get the distance. Let's get the position of ourselves. So we'll take out a get position chip. And then I can also get the position of the shape as well. So we're going to get the position both of the shape and of like ourselves, the local player. So we have this. This is an any port. It's not any, it's like player object. So let's take out, it doesn't like know to default to local player. So we'll take out the get local player chip and hook that up there. And what we want it to do is move in the direction from wherever it is to where I am. So that is a direction, right? Like there is a direction that exists from the object pointing to wherever I am. And like the way you can calculate that is you take the position of the object and you subtract the position of myself. And that will give you like the vector in between us, kind of pointing from the object to myself. So we'll take out a subtract chip. And as I mentioned before, this works same with vectors as it does with everything else. Cool. So that is some vector. This is a, like as I move further away, the vector gets bigger because the distance between us gets bigger. So that makes sense, right? If we want to use this to move it toward us, we don't care how far away I am. We only care about the direction. So we can scale it down, or even better, let's just use clamp magnitude. Cool. So this will limit how much we want to move. Right now we're calculating how far we want to move it each tick of the 30 hertz chip. So let's max this out at maybe like 0.01. So it moves 30 times that, 0.3 meters a second. Cool. So that is some vector, some fixed distance between me and the object facing toward me. So let's take out a set position chip. And we have the object. Let's hook that up to target. Just going from Rec Room object get first with tag. This gives us the object that has a reference to the shape. And we're going to wire that up into the target port of set position because that's the object we're going to be moving. Additionally, there is a position. We have that here. Oh, no, this is not the position. This is how far we're going to move. So let's add that to the current position. The vector 3 add, or just a regular add, I mean. So let's take the current position of the object, which we already have right here, wire that into one port of the add, and then add that direction offset we want to apply, and wire that into the position, and then we'll hook it up to.
You kind of have it the.
Oh, everybody's running on it. We need to check this against the authority. That's right. So let's disconnect that and check if we are the authority of the object. That is fortunately quite simple to do now that we know how networking works.
I think also it's going away from you.
It's possible to have it backwards. We'll see that in a second.
I was gonna say the position needs to be like X.
There are too many chips for this. Let me find it real quick.
Are you trying to get like recommend object, get local player?
Local player is, let me find it through the filter so I can remember what it's called.
Oh, okay.
Rec Room object get is local player authority. There we go. That's what we wanted. So this takes an object, a target object. Let's hook that up to what we have here on the tag, and it gives you a result. This will be true if you are authority over the object. It will be false if you are not. So this way, I was the last person to touch the object with my maker pen, so I'm the authority over the little triangle. So let's hook that up there, and then through here. Yeah, it is going the other direction. So fortunately, that is very simple to do. These two values here are just the wrong way. So let me switch the way we have the subtract port set up, and it will move toward me. As I move over here, you'll see it changes directions. Right now, this is, let me go in front of the camera so you can kind of see it a little bit better. And you'll see it's moving up. It's actually moving fully three-dimensionally. So, and then once it gets to me, you'll see it stops. When you get the position of a player, that is the position of their feet. Like even if they're a bean avatar, it'll be the position below them.
You hearing errors?
Are you guys getting errors?
Yeah, I'm hearing beeping.
Oh, I'm getting errors as
Wait,
well.
Hang on, I know. Wait.
I don't think that's coming from here because the chips
Yeah.
are none of the ones I have.
Yeah, it's this one. Oh,
Oh, do you have something configured incorrectly?
no, there's just no tag.
Okay, cool. So this looks good, but we could probably make it a little bit better. What if we don't want it to move up and down? Like for instance, you're most likely going to be running on a flat surface. You're not going to be like, like flying through the air. So like for instance, if you jump up and down, it might be kind of weird if the AI jumped up and down at the same time as it's chasing you across the floor. So let's do that. Yeah, what's up, default?
What is that set position
okay.
chip connected to?
So the set position chip I have here, this of course is
For
first
the
connected to the exec, so this makes it run. There is a target port. This is the object you want to set the position of. This is the Rec Room get object first with tag. This is getting a reference to our shape. So that's what we're setting the position of. And then the position, this is the new vector coordinate in the room that we're setting, that we want to move the object to. I'm moving it very closely to, like, every time this runs, it's only moving a little bit further from where it is now, so it looks smooth. But really, these are all just independent coordinates. I could be teleporting it all around the room really quickly if I wanted to. Does that answer what you were wondering about default?
Yeah, I was just wondering like where it
Cool.
was connected to.
Okay, so if we don't want it to move up, let's clamp this along the Y direction so it doesn't actually move up and down. And we can do that with a couple of the chips we saw earlier. Let's take out a vector 3 split. Let's put this before we clamp the magnitude, or before we add it, I mean. So it just keeps whatever velocity it's currently at. So this will take the vector, split it up into a float for X, a float for X, and for Y, and a float for Z. This might seem kind of counterintuitive, but we're now going to take out a vector 3 create to now immediately create a new vector. And we're going to hook this up almost exactly the same, except we're going to skip over the Y. The Y value is going to be the same. We're going to copy over the X value. We're going to copy over the Z value. X is just, one horizontal direction. Z is the other horizontal direction. Y is up and down. We don't want that one to change, so we'll just leave that how it is. And then we'll hook that up here. And now you'll see it doesn't actually move up and down. Might be kind of hard to see on the video, but the shape is just staying at the same level. Like no matter where I go, it's just going to stay that same height. I could go like way down below, and it'll figure out the point directly above me and move there. Cool. Now, there is a slightly simpler way to do this. If you were looking closely at those chips we were seeing earlier, one of them might make sense. One of them was called vector 3 move towards, which is doing exactly what we're doing here. This takes a current position, and a target position, and it moves a fixed amount over there. That's exactly what we're doing here, except we're doing it manually, just to illustrate how it works. But we can change the system to use the chip, so it's a little bit simpler. Right now, we're moving 1 centimeter, 0.01 meters every tick. So I'll set that as the max delta, the same way it is there. Cool, and our current position is just the position that we're in now, like wherever the object currently is, that's our current position. So let's just wire up the get position of the shape into current, and similarly, target is just where like I myself am. So let's just take the position of myself, and that's that new, instead of having to do this math, that's just the new current value we want to go to. So let's hook that up to position. Not sure where it's going. Oh, somebody else configured it. So they stole authority from it. So let me just click it and take it back, and you'll see it's moving toward me again. Anybody who touches it with the maker pen, you'll steal authority. So let's, yeah, you can see it's moving toward me now. I can just delete all these extra chips now that I don't need them anymore. This one, this one, this one. What I can do is still use the same idea here to clamp the Y. And we'll just set that position. So it's doing the same thing. We're at about 100Y, so let's just manually type in. It's just going to set to 100Y every time. Right now it's like way below us. Cool. And now if I configure it, it'll move toward me again with a little bit fewer chips, staying at the same Y. Cool. Oh, one last thing. We can still improve this a little bit further. So if you look closely, this is running at about 30 hertz. So this will be about 30 times a second. And every time this runs, every about a 30th of a second, it will run again. We are moving it this far. We're moving it 0.01 meters. That's about 1 centimeters, which means it's moving at about 30 centimeters per second. However, if you are on a low-end platform or you're getting lag, maybe there's a lot of people in this room, this won't run at exactly 30 times a second. This could start to take a little bit longer. It might run, if you're on like a Quest 2, for example, or a phone, this might run, as low as like 10 to 15 times per second, which means that we're only moving, we've gone from moving 30 meters per second for the cube to now moving about 15 centimeters per second. So that's a lot slower. But we can actually like change that, because like we don't want the cube to slow down. If you're on a lower end platform, we want it to move at about the same speed, which means if you're not running this as frequently, you have to move it further, right? And fortunately, there's a simple way to handle this. There is a delta time property. If this is running at exactly 33 hertz, 30 times a second, this will be exactly 1/30th of a second. However, if you're running slower than that, this delta time value will get bigger because there will be a longer amount of time before runs. So if I just take this value and I hook it up to max delta, and let me configure it so I am authority again. This is now normalized. It's running at exactly 1 meter per second, just because like this value here is like executions per second, and then I put that into move towards. It'll go that far per second. Cool. So that's how you do that. Any questions about that before we move on to working on our own assignments? Yeah, what's up, Wolf?
It's about the event receiver for delta time. Does delta time kind of increase depending on the amount of people are in the room? And if so, how much?
It can, yeah. So ideally that will run exactly 30 times per second every time. If you are experiencing lag and your computer cannot keep up with that, maybe it's like your computer is doing a lot, which can happen if there's more people in the room. It's busy doing other things, so it can't spend the time to run this exactly every 30th of a second. So this delta time can get bigger. If it's like getting laggy, it might only be 15 hertz, half that, which means this delta time will be twice as big as it is when it's exactly 30 hertz.
Okay.
Cool. And I almost figured out there's actually one thing we want to change. So you'll see, if I could configure it, and please could nobody configure it again. I think somebody has it selected. There we go. So it'll move back toward me now that I'm authority. You'll see that like if I were to put like some sort of enemy character or like a pet or whatever on this, it's facing the same direction, like no matter where I am, it's not moving toward me. I mean, like the object is spatially moving toward me, but like it's not turning to face me. So there's a pretty simple way to fix that. Let's take out a set transform chip. Transform, just as a concept, refers to how the object exists in 3D space, which includes the position as well as the rotation. And that's exactly what we want to do. We want to set the rotation. So let's just disconnect this first. We have an exec. We'll hook that up in a second. We have a target. That's the same thing. That hasn't changed. Let's just hook that up to the object. We have a position. This also has not changed. Let's just hook that up there. We have a new port. This is a rotation. This takes either a direction vector or a quaternion. Quaternions are another way to represent rotations. We're not going to use those here. But the direction vector is just the vector that faces from the object to me. So we can actually just, I think, take the, see what some of the chips we had before doing the subtract. So let's take that subtract out again. And then the position of me minus the position of the object. Wire that into rotation, and then hook up the exec again. And that is not working. Let me look at this. Let me see what this value is. Oh, duh, I haven't connected it. Okay, cool. So now you'll see that that's actually like following me. It's turning to look as I turn around it. And similarly, you'll see like maybe you don't want it to look up and down. You just want it to look, left and right. You could do the exact same thing we did here, where we just cut out one of the components. You could do that with rotation, just the same, and then it wouldn't look up and down. It would just look whatever directions you'd like. But cool. Yeah, that's how you do that. What's up, Crypto?
Oh, and Will, don't forget to breathe.
Good point.
Yeah, I did that.
Oh, so if you only want it to go up and down, so just along the Y, that's exactly the same process we've done here. Right here, this is only moving in X and Z. It's not moving in Y. It's just constant 100Y. If you wanted it to only go up and down, you do the same thing, except you would disconnect. You do it in reverse, basically. So you would connect these ones. It's going to be at 0, X, and Z. So that's somewhere in the room. Let me take out another split so it'll be the same. Same X and Z as I am. Cool. So this is kind of cheating because it's just like directly jumping to where I am in X and Z. But as far as the pathfinding goes, or at least like the basic AI logic, it's just following me in an up and down direction. Cool. Any last questions? Okay, great. Let's get to the example. So what you guys are going to build today is, so if you've ever seen a game, sorry, what was that?
I said, was this not the example?
Oh, yeah, sorry, this was the example. You guys are going to work on your own assignment now. So what you all are going to build is, so if you've ever seen like The Sims, the popular PC game, there is a green shape above your head. You all are going to build a small shape, which similarly is fixed above your head. As you move around, it will stay above your head. You don't have to do this logic where it will move. It can just jump directly above your head. Ideally, it should do that. If you do that, also when you make it above their head, it shouldn't just be like their head and then like up. So like if you turn your head, like we don't want it to be over here. We want it to just be like directly above them. It would be kind of weird. So just get the head position. There's a chip to get your local player head position. You're going to use 30 hertz. You're going to get the position of the shape. You're just going to set it to be up there. Use a vector offset. Use like the add chip to just go up a little bit, increase the Y. If you do that, you got that working. You could even animate it if you'd like. So use a sine chip. Power that like paths like time into the sine chip. That will give you a nice curve up and down. You can use that to animate it to kind of make it like bob above your head. You have to do a little math to get that, but don't worry about that until you get the main logic working. And then if you finish that, come ask me for anything else you can change. Cool. Does anybody have any questions about that? Awesome. Everybody go get started.
Wait a second, can I just use what I have right here and then just kind of edit it to what I need it to be? Oh, yeah.
Hold on, I have to turn off my teacher mic 1 sec.
You play The Sims too much, don't you? You look like you would.